Hi, welcome to this lecture on hypothesis testing and confidence intervals. This is a fascinating topic, although the title does not seem so. And this is a very important concept, not just within machine learning, in the entirety of data analysis. So I want to make this lecture into kind of like a standalone lecture because of its nature. You don't need too many prerequisites to understand what is being discussed in this lecture. But yet, this lecture is again part of the Foundations for Machine Learning course, especially where we are currently covering statistics and probability for ML. So before going into the mathematical details of this lecture, I want to show you a simple case. So let's say there is a company who is manufacturing batteries. And say they have manufactured 500 batteries and they tested the average battery capacity in terms of number of hours, like how many hours can their battery last. Now, this could be an electric vehicle, like a car battery manufacturer, right? And it's very important for their battery life to be as high as possible. Now, this company, let's say, for some reason, they did not get, they did not get to make very good batteries. So their actual battery data, battery duration data, it may look something like this. So here you have battery serial numbers ranging from 1 to 500 and 1 to 500. So the serial number is in the first column. The second column is the battery duration in hours. This is the real data that this company, let's say, collected from their own experiments. And in this real data, they have, let's say, a mean of 79.5, meaning roughly 80 hours. The battery can last only 80 hours. And standard deviation, the real standard deviation is 10 hours. So 80 plus or minus 10 hours, roughly, right? Now, the problem with this data is that, let's say, the company was aiming to produce cars whose average life duration is 100 hours. So this company is conducting some fraud. What is that fraud? What they're going to do is they create some manipulated data. And the manipulation that they have done is to every single number here, to the every single actual data, they added a number of 20. So here in this Excel sheet, I have added 20 to 67 to make it 87, 20 to 79 to make it 99, 20 to 86 to make it 106, such that the manipulated mean value for battery duration now is close to 199.5. Standard deviation remains the same. So now instead of the battery life being 80 plus or minus 10, now it became 100 plus or minus 10. But this is manipulated data. Now, let's say you are a person who is supposed to test some of these batteries from this 500 batteries, and you want to conclude whether the claim of the company that they can produce batteries with 100 plus or minus, let's say, the mean average battery duration of 100 hours, you want to test whether that claim is true or it's falsified. Let's say you are tasked with this. Now, how would you test this? Are you going to select all the 500 batteries and are you going to test each one of them for its battery duration? It's impossible to do that because maybe they have, instead of 500 batteries, maybe they have 500,000 batteries. Maybe they have 5 million batteries. Who knows? So you can only test a sample from whatever they provide you. So now let's say this company will provide you 50 batteries randomly. So you can go to the company and select 50 batteries from their let's say inventory, and you can conduct some tests on that so that you will get the actual battery duration for those 50 batteries alone. You will not get to know about it for the remaining 450 batteries. So what do you do? Let's say these first 50 ones with serial numbers, these random serial numbers ranging from somewhere to somewhere. These are the batteries that you get. You go and collect from the inventory of the company and you do rigorous testing. At the end of the testing, what would be the data that you will get? The data that you will get will be real data because you are not conducting any fraud or manipulation. You are directly testing the battery duration, which means whatever the company got in the beginning in their original test, similar data only you will get. You will not get this manipulated data where a factor of 20 was added to every single battery's duration, right? So now the question is, okay, let's say from the sample that you collected, from the 50 sample batteries that you have, if you have this kind of a distribution, and this distribution is surprisingly showing you a mean value somewhere around 80, can you conclude that the company was conducting fraud? Because the company is claiming that for them, their average battery capacity is 100, and they have 500 batteries. They have manufactured 500 batteries. You, on the other hand, you took random 50 batteries from their inventory. You conducted testing, and you got a data distribution like this, whose mean value is 80. Now, is there a way for you to confidently say that the company is conducting fraud? Or do you give the benefit of doubt because you have not tested the remaining 450 batteries? What would you do in that case? This is exactly the kind of the role of hypothesis testing and confidence intervals. It's a very fascinating topic, and I don't want you to not focus on it just because its name sounds boring. So this is very commonly used in machine learning for testing the assumptions or validating machine learning models. It helps us make decisions about data. It helps us interpret results when someone is presenting you with something, or when you are yourself presented with some results. So this is very, very, with just this battery example itself, I hope it's sufficiently clear for you. So hypothesis testing, in formal terms, it is a method to decide if the claim about a population is supported by the evidence from a sample. In our battery example, the population was the entire 500 batteries. The sample was just the 50 batteries you collected. The evidence from the sample was the actual testing you conducted on those 50 batteries and whatever data you got as a result of that test. And the claim is what? The claim is that of the claim made by the company, who said that for their 500 batteries, the average battery life is around 100. So now you want to check if that claim is true. If that is true, how do you quantify? If that is not true, how do you quantify that? And that comes under the category of null hypothesis and alternative hypothesis. So null hypothesis is the assumption that whatever you are told is true. Meaning this is the default assumption. So if the company is telling you that the average battery lifespan is 100 hours, the null hypothesis states that H0, so that's the notation for null hypothesis. In H, according to null hypothesis, the mu, the mean value of the population, the distribution is 100 only. You kind of assume that. But you also create an alternate hypothesis called H1, and you are testing basically your alternate hypothesis against the null hypothesis. Now, the alternate hypothesis in this particular case is that the average lifespan of the battery is not 100 hours, meaning mu not equal to 100 is your hypothesis. Now, you want to test whether this H1 is true against H0. So, if the null hypothesis is true, that means this H0 is true. If alternative hypothesis is true, then H1 is true, not H0, meaning the mu, the mean value, will not be 100. It can be greater than 100 or it can be less than 100. Now, how do we formalize this? Let's see. Now, there can be two situations here. One is the battery lifespan is, let's say, 80, which is less than 100, the claim made by the company. The other case, the battery lifespan is 120, in which case it's very good. The lifespan is much higher than what they claim. But in some cases, in some experiments, like let's say you are doing a drug discovery or you are trying to identify the right dosage for a drug, a higher dosage or lower dosage, both are not good. So there are cases where you really want the mean value of the population to be same as what it claims to be. So this is how it works. Let's say H0 is true, meaning null hypothesis is true. Then you have to use your data, which is sampled from the original population, to test whether there is enough evidence to reject H0, meaning whether the claim made by the original null hypothesis, whether it is true or not. So you either accept H1, so accept H1, or you reject H1. So you're either, not H0, H1. So you either, at the end of the day, you have to either accept the alternate hypothesis, which is the case that mu is actually not equal to 100, or you have to take the null hypothesis, in which case mu is actually equal to 100. So there are two numbers here that you have to be familiar with. One is called the significance level and one is called the p-value. So the significance level is denoted by alpha, p-value is simply p, and usually the cutoff for alpha is defined to be 0.05 or 0.01. So 5% or 1%. So here essentially what you are saying is that here alpha can be 5% or 0.1%. And what this means is you are allowing a 5% chance for you to be wrong when you are, let's say, rejecting the null hypothesis, or you are allowing a 1% chance to be wrong when you are rejecting the null hypothesis. So these are the typical values of alpha that people take when creating the null hypothesis, when people take the significance level. The second thing is p-value. Now we can learn about all of this with a simple numerical example. So the question is, if in reality the batteries were to last 100 hours on an average, meaning if the H0, which was the null hypothesis, if that is true, how likely are you to observe a sample mean of 98 hours? Meaning you sample 50 batteries from the 500 batteries. How likely are you to observe a mean of 98, or let's say a mean of 80, if your actual null hypothesis of 100 hours were true? This is basically what you're looking at. And the best way to understand this is, rather than going into mathematics of it, I want to first show you some graphs. So let me go back to the Excel sheet. In the Excel sheet here, you can see that this is how the distribution was for the real data. This was the battery life according to the original experiments conducted by the company. And according to these original experiments, the mean value is somewhere around 80, as you can see by this, based on this blue bar graph. So the mean value is not exactly 80, but somewhere around that. When you calculate the exact mean value, here it is 79.5. Now, what the company did is they manipulated the data by adding a number 20 to the entire data set. So now the batteries, now the company is claiming that the battery, on an average, they have a mean something that looks like this. So ideally, if this was true, if the battery life distribution was like this red bar plots, and if you are sampling something from that, the mean of the sample also, in the highest probability, it should be also somewhere close to this, which is 100. It cannot be close to 80. But according to your experiments, you are getting the mean close to 80, right? That's what is happening. We can look at this once again, because see, this sample was randomly selected by me from this list. I did not selectively select. So any 50, so if I select from here to here, 50 batteries, let's say from here, and if I plot the, let's say the mean of that will also be 50 only. We can see that. So in the highest probability, if you are sampling 50 items from this 500, its mean cannot deviate too much from what the actual mean of the data set was. And the actual mean of the data set was actually 79 or 80. So when you conduct actual tests on this battery, its mean also can be close to 79, 80. It cannot be 100. So this is where you have to quantify how likely is your null hypothesis to be true. So now here is how you mathematically do that. First, you calculate the p-value, where p-value is the likelihood for your data sample to be within the range. So let's say if alpha is equal to 5%, right? And if this is your distribution, then if alpha is 5%, then there is a 2.5% here and 2.5% here. And if the sampling is such that the probability for your the mean value of your distribution is less than alpha, less than 0.05, then you reject null hypothesis. Because if the mean value has to be less than this alpha, then all of your values has to come from a minority. So here is another way to think about that. If the mean value of the batteries that which you are actually collecting from their inventory, if that mean value has to be close to 100, then by luck or by chance, you have to select only those batteries which are, you see these blue bars, which are the actual batteries which somehow happen to have close to 100 mean. So for example, the real battery, this real battery had 104 as the mean life. This real battery had, for example, let's say, there are very, very few number of batteries with mean life close to 100. This one, not mean life, the actual duration, 100 hours. There are a few more batteries like that. For example, this has close to 97 and few more. So this has 99, 99. You see, so your random picking has to be such that somehow you end up randomly picking the best batteries from this plot. Only then your sample mean will become close to 100. Otherwise, your sample mean will inevitably be close to 80. And this null hypothesis is a way to quantify that. So, for example, if you have a p-value of 0.12, that means there is a 12% chance of seeing your data if null hypothesis is true. Meaning if there is a 12% of observing whatever sample data that you observed if the null hypothesis were supposed to be true. Let me mention this in terms of the battery example. If the companies claim that batteries have 100 hours of average duration, if that is true, then there is only 12% chance or X% chance that in your distribution the mean will be observed as 80. There is a much higher chance that if this was true, there is a much higher chance for you to observe a mean value of 100 hours rather than 80 hours. There is a 12% chance for you to observe 80 hours. There is maybe, let's say, 40% chance. This I'm randomly saying 40% chance for you to observe 100 hours, etc. Right? So this is an example of how you can interpret p-value. So in this case, you have only 12% chance for seeing your data if x0 is true, but then the cutoff you are defining here is alpha equal to 0.05 and alpha is less than p in this case. So you don't reject null hypothesis in this case. In this particular case, you assume that, okay, that the threshold that I had decided for rejecting the null hypothesis, meaning rejecting the original claim, was 0.05. And I am in my, like, according to my data set, although I'm getting a mean, which is very different from what is the claimed mean, there is a 12% chance for that to happen. And I'm okay with that. So then you don't reject null hypothesis. But if you reject null hypothesis in this case, and let's say the null hypothesis happened to be actually true, then there is something called as type 1 error. In another case, there is called as type 2 error. So in one case, you reject null hypothesis when it is true. In the other case, you accept alternate hypothesis when it is false. Or the opposite of that is, you reject alternative hypothesis when that is true. The first two things which I said was the same thing. I flipped it. Basically, in one case, you reject null hypothesis when it is true. That is an error. In the second case, you reject alternate hypothesis when it is true, meaning you accept null hypothesis when it is false. That is also an error. So these are called type 1 and type 2 errors. These are just formal terms, but at the end of the day, it helps you debunk false claims by having a sample data. If people say that, let's say, Indians on an average, their height is, let's say, 7 foot or 6 foot 5 inch, then you can test with some sample data to kind of debunk or to approve that claim. Because you can't test with 1.4 billion Indians, you test with maybe 1,000 Indians, 10,000 Indians, or 50,000 Indians, and you can do a hypothesis testing. You can create a null hypothesis. Null hypothesis will be accepting the claim that Indians do average, on an average, they are 6.6 foot, 5 inches tall. The alternate hypothesis is that they are not that tall. Either they are taller than that or they are shorter than that. And you will come to conclude that alternative hypothesis is true in that case. So this is just a mathematical explanation of this term, but at the end of the day, it's a very logical thing that will help you. So that brings us to the end of this lecture, and this was a very important concept, which I'm pretty sure is also going to help you while building ML models. So thank you so much. We will meet again in the next lecture. Take care until then. And I once again congratulate you for covering the course up until this point. Stay with me, and you are on a very, very good learning track now. So see you again in the next lecture. Bye.